This is Premier Aerodynamics podcast number 20, and today we're talking about the effects of tornadoes on structures, so buildings. And to do that, we're going to be looking at a paper called Vulnerability of Roof and Building Walls Under a Translating Tornado-like Vortex. And this is open access. You can find the link in the description below. So they talk about a vortex and that these tornadoes create and how these vortices affect the pressure on a building, on its structure. And they say, for example, in the abstract, earlier researchers have investigated extensively on building models exposed to stationary type vortex generated in a laboratory type tornado simulator. However, studies using translating type vortices are few. So up until today, or this date that was published, most of the time the tornadoes that were being simulated in wind tunnels had stationary vortices instead of a translation. And obviously a tornado doesn't just stay in one spot, it moves around. So a translation in the vortices that it creates is necessary. And this does create a difference to the flow physics as they go on and say. And then they go on in an abstract and they say, however, studies using in the present investigation, the external and internal pressures experienced by a building model are discussed based on experiments conducted using a translating tornado-like flow simulator at Tokyo Polytechnic University. The swell ratio, which characterizes the strength of vortices generated, is kept constant. So that's the parameter that they're using to characterize these vortices, the swell ratio. Often you'd use something like the circulation or the vorticity, something like that, or you could even use the Q criterion or whatever, but they're using the swell ratio here. The investigation attempts to explore the opening locations, which can result in higher internal pressures and net roof forces in building and the vulnerability of roof structures of buildings when exposed to tornado-like flow. And the results indicate that there is an increased amount of internal pressure fluctuations at higher translating speeds. So what they're saying is when this vortex moves around more, you get a higher internal pressure fluctuation. So talking about some of what's been done before in other literature, they go on and say Sengupta and others investigated the transient wind load effects on a cubic building model in a microburst and tornado using large eddy simulation. Their investigation revealed that slowly moving and smaller sized tornadoes produced higher peak loads. So the slowly moving part, that makes sense. If you have a slow moving tornado, it hovers in one spot longer. That's going to create more pressure, or it's going to affect the area more. The smaller sized tornadoes, that's quite interesting. It must mean that it's somewhat concentrated, or perhaps because one location of the roof is in a higher concentrated vortex, perhaps. Who knows? This also reminds me, we also have another podcast on this kind of phenomenon. It's not exactly the same, but it's similar. It's podcast number 3 with an associate professor called Luca Caricoglia. So check that one out. So in this paper, they go on and say attempts have been made to understand the effects of tornadoes on structures by mimicking their behavior in laboratories using tornado-like flow simulators. Some of these simulators have the ability to produce stationary vortices, which, as we discussed, is not ideal because tornadoes are translationary, they are dynamic, but others generate translating tornado-like vortices, so those ones are a bit better. And some of the observations related to the interaction of buildings with tornado-like flow include the symmetric nature of the pressure distribution on the sidewalls of a building engulfed in a tornado-like flow. So if the entire building is inside a tornado, there's a symmetric nature of the pressure distribution on the side walls, not the front or the back, so the windward or the leeward, respectively, but just the two sides. What's more, very high negative pressure coefficients on the roof surface occur compared to the sidewalls, so you do get this a lot more suction on the roof. It's like pulling the roof off, which does happen a lot. Like when you ever see pictures of buildings that have been hit by tornadoes, often the roofs have been popped off. So the leading edges to the flow experience higher negative pressures compared to the trailing edges when exposed to a stationary vortex. Now, they also investigate this in this paper for the translating vortex, and they will come up with their own conclusions, and we can compare them later. And real-time studies give an account of the combined translating and rotational nature of tornadoes. Thus, to better understand the nature of tornado structure interaction, the translating nature of tornado vortices also needs to be considered and the pressure coefficients on the building surfaces and internal needs to be determined. And then they go on and talk about another study, and they say that this study revealed that the peak loads varied with the eave height, plan area, aspect ratio, and other changes in the geometry of the low-rise building structure, which makes sense. If you change the way that the building is structured, it's going to affect the strength of it and also how the tornado moves around the building. And then another group of researchers, Cow and others, investigated the effect of tornado-like vortices on a cooling tower. They found that the pressure drop accompanying a tornado dominates the pressure coefficient magnitudes for the cooling tower when located at the tornado core center. So, in other words, with all these different studies that they've been looking into, tornadoes, whenever they hit something, they create this massive low pressure, this suction, and often it's on the roof and on the leading edges, and often the sides experience a very similar change in pressure. So they're quite a bit more symmetric, whereas the upstream and the downstream faces have very different pressure distributions, as they'll get into. One of the commonly occurring failures include the separation of the roof sheathing from the roof framing members, as we mentioned earlier, because you have that low pressure, it pops the roof off. Positive internal pressures and large uplift wind forces acting on the roof cause these separations. These are found at the roof corners or ridges where the wind-induced effects are greatest. So that's interesting. It's at the edges, not in the middle. So they go on and discuss their experimental setup, and this is quite interesting because they do have this in translation in the vortex. They have a different setup to stationary vortices. And they go on and say the experimental setup used for the present investigation comprises of a translating tornado-like flow simulator. And then they go in and describe it a little bit. They say it comprises of an updraft system equipped with an axial flow fan capable of diverting the surrounding air into the confluence region, which is converted in together at the center of the vortex before ascending. I'll explain a bit more later what this means in layman terms because this is a bit technical how they talk about it. They go on and say the convection region houses a honeycomb structure that removes the vorticity as the flow ascends up. So that's pretty common. In most wind tunnels, you do get a honeycomb section. Sometimes, like really the only wind tunnels that I'm aware of that you may not have a honeycomb is for atmospheric wind tunnels, but even then you usually will have a honeycomb. So pretty much every wind tunnel will have a honeycomb. They go on and say the updraft system has two layers, which enables the flow that ascends up to return as a rear flank downdraft. Rear downdrafts are a common feature in naturally occurring tornadoes. So let's discuss this contraption a little bit more just in layman terms so we can understand it better. So for those of you who are watching, there's a picture here. For those of you who are listening, I'll describe what it looks like. So imagine a UFO effectively, that quintessential UFO type of looking shape. That's kind of what this is like. In the middle, you have the central shaft, which is where all the air gets sucked out from. It gets sucked up, and that's through a fan there. Then the air goes around the edges of this UFO-like structure, and then it hits the ground. It comes down and hits the ground, and then that flow rushes in to the center and following the ground plane, and then gets sucked back up, and it goes around in that kind of loop fashion, and that creates the vortex, and it's a translation vortex, so it's dynamic. And with their contraption, the floor of the simulator can be adjusted to obtain different inflow heights using a pneumatic arrangement. The length of the simulator floor was 2 meters over which the tornado-like vortices translate. So that's pretty big. The radius of the updraft hole was 225 millimeters, and the inflow region had a height of 160 millimeters. The outer diameter of the updraft system was 1.3 meters. The required angular momentum for the inflow is provided by the guide vanes at the periphery of the updraft system. Now, one interesting thing that they talk about is something called a laminar vortex. So they go in and say they say a laminar vortex here refers to a rotational flow with a small or moderate swell. So that's pretty interesting because when you think about a vortex, no one really ever thinks about a vortex being laminar. It's often like translationary or it's often turbulent. But Sorry, there is some background noises here at our lab. So if you hear them in the background, just know that it's just the lab going on. Anyway, so the laminar vortex can occur when you have small or moderate swirl according to their definition. The central core is observed to be smooth and laminar as seen from the flow vis, as they have in this figure, which I'll explain in a second, and the core extended to the full height of the experimental volume with very little spread of radius with height. So this figure here, which for those of you viewing this is figure 3, for those of you listening to this podcast, what this looks like, effectively imagine like a jet of air just impinging the ground. That's kind of what it looks like. So you get this jet hitting the ground, and then it spreads out radially kind of thing. Now, obviously this is the opposite occurring, but this contraption makes something that looks very similar to this kind of phenomenon. So now you get a bit of an idea of what it looks like. So the translating speed of the updraft system, which mimics the translation of a tornado-type vortex, was varied from 20 to 240 millimeters per second. So that's obviously because this is a scale model, and when you scale that up, the translating speeds observed in an atmospheric tornado is of the order of 10 to 30 meters per second. So the scaling is adequate for this kind of speed. The translational velocities were normalized using the corresponding maximum updraft speeds, so they were effectively non-dimensionalized. And now they go on to scaling considerations, and this is one thing that's really interesting for dynamic systems. So again, in podcast number 3, which I mentioned earlier, with Luca Catacoglia, associate professor, he was discussing about how they make a similar kind of a phenomenon, a downdraft. And because downdrafts are dynamic, as are these tornado vortices, you need to not only scale in the spatial way, but also in the temporal way. And this is what they do here. With the spatial way, they just say that the building was scaled to a ratio of 1 to 1,000. And then they go on and talk about some of the temporal ways that they do it. I'm not going to go into the mathematics of it. If you're interested, you can look at the paper. It's a little bit intense for the math. But they go on and say, if the tornado vortex is scaled in the same ratio as that of the model scale, the generated tornado in full scale will have a radius of the order of 36 meters, which matches those reported for tornadoes occurring in the mainland of Japan. And then they go on to their results and discussion. And they say, experiments were conducted to determine the nature of external and internal pressures experienced by building model when exposed to a translating tornado-like vortex. The following experimental cases were considered to capture the behavior of pressure variations on building models. 1. Variation of external pressures on the building model surface for a range of translating speeds was obtained for fixed swirl ratio. So they changed how quickly these vortices moved around, but they had the exact same swirl ratio. So that's pretty cool that this contraption that they have, their experimental setup, can fine-tune parameters such as the translational speed while keeping the swirl ratio still the same. The second case that they looked into, the variation of internal pressures was obtained, keeping independently open the dominant opening on any one of the 4 side walls. This was repeated for a range of translating speeds, but for a fixed swirl ratio again. And finally, number 3, the resulting net roof pressure coefficients were also calculated. So, for their results, they say that it can be observed that irrespective of the translational velocity considered, the building with the windward opening, so if you have effectively a door open on the front side of the building, it registered a higher negative pressure coefficient compared to a similar opening on the side walls or the leeward side. So having the door at the front increases this negative pressure coefficient, which is not a good thing. You want to reduce this negative pressure coefficient to reduce damage to the building. At any translational speed, the maximum percentage difference in the value of the internal pressure coefficients obtained corresponding to the opening on the different walls was the order of 75%. So this shows that compared to having this opening at the front, having it on the other walls was only like 75% of the max kind of thing. So having the opening on the front is much more damaging in practice. They also go on and say it can be observed that the roof corners experience the greatest suction compared to the pressure taps located on the windward wall corners near the roof edges onto the translating vortex. So that's pretty interesting. And similar observations were recorded for the roof corners in the leeward side and the pressure taps located on the leeward wall of the translating tornado vortex. These results indicate that the roof structures are more vulnerable to tornado effects compared to the side walls. So again, as we were mentioning earlier, the roof experiences a lower pressure, so there's suction compared to any of the walls. And that's why the roof often pops off. As can be observed in figures 9 and 10, the magnitudes of the external pressure coefficient on the windward face and roofs were comparatively higher in magnitude compared to the corresponding pressure taps on the leeward side for all the translational speeds of the vortex. So let's have a quick look at figures 9 and 10. So pressure taps 5 and 6, if we go to their setup, 5 and 6 were the leeward side, and then 7 and 8 were at the back, and then 1 and 2 were the windward, and 3 and 4 were the top on the roof. So 5 and 6, which are these circles and asterisks, they have a much their external pressure coefficient is much closer to 0 than the pressure taps on the roofs, which is much lower. So you're getting a massive suction happening. So continuing on with their discussion, they say it is to be noted that the difference in pressure coefficients between the roof and faces become more predominant at higher translational speeds. So this is kind of intuitive. If you have a tornado going much faster over something, you're going to get a far more dynamic response. So the roof will be affected perhaps very quickly, and then everything is changing so rapidly that you have a very big difference. Whereas if you have a tornado hovering over something, perhaps everything will be affected somewhat in a similar way, or at least more similar way than if it was very quickly going over. So, analyzing the external pressure coefficients experienced by the side walls, it can be observed that the windward edge of the side wall experienced almost comparable pressure coefficients with the leeward edge of the side wall for lower translating speeds. The difference became considerable for intermediate translational speeds observed. So if you bumped up the speeds this is going over, again, you're getting a very dynamic response. So there are going to be differences. Analyzing the lowest minimum net roof force coefficients for openings located on different side walls, on figure 12, it can be observed that at lower translational speeds, the roof experienced higher negative net force coefficients for openings located on the side walls, whereas for higher translational speeds, the tornado vortex, the opening on the windward side produced the higher negative net force coefficient. So that's really interesting. So it's saying that depending on how fast this vortex is moving, how fast the tornado is moving over this object, the building, it's going to determine whether you're going to get a much lower pressure on the front face or on the sides. So there's this really dynamic effect occurring. It's not a one size fits all, so it really depends on how fast this tornado is moving. So before we go any further, I just want to say, make sure to check out the instruments we make here at Premier Aerodynamics to make your experiments better. We make the Atmosphere Hawk, which greatly helps reduce errors in your experiments. We also make a PIV system, which is really good. And we're also bringing out a couple other things, so stay tuned for those. Check out the International Aerodynamics Conference we put on every year. It's there for all aerodynamicists to get together and talk about aerodynamics. And check out the courses we put on to make you a better aerodynamicist. Links to them can all be found in the description. So moving on, in summary, they say that one, they found the roof of a building exposed to a translating vortex is more vulnerable compared to the side walls, as observed from the external pressure coefficients and the net roof force coefficients. So that's in agreement with the stationary vortex that they were discussing earlier. You know how I mentioned that there were other papers and other research groups that looked at they could only make stationary vortices, and they found very similar thing happening there. So a translating vortex doesn't affect that too much, it seems. but this still you're going to have a much greater effect on the roof of a building than the side walls. The second finding that they had, the windward wall of the building to the translating vortex experienced a higher negative pressure coefficient compared to the side and leeward walls for any case of translating speed of the vortex considered. They also found actually, but at very low speeds, that the side walls had a high negative pressure. So I think they didn't say that in here. And the third finding is it was observed that when the opening was located on the windward wall of the building, the internal pressures recorded were highest. So if you're going to if you're going to build a building, make sure to put your door on the side wall or the back wall if you can somehow predict which angle the tornado is coming in from. So overall, that's how a tornado affects a building. And the main takeaway is that it really rips off the roof of the building because of the low pressure that you have on there. The side walls and the rear wall are not so much affected compared to the front wall. And also you want to put the door of your building on one of those walls to reduce the loading effectively on the building. So that's it for this podcast. Make sure to like and subscribe and check out everything we do here at Premier Aerodynamics. And I'll see you in the next podcast. Peace out.